This is a power supply I picked up a couple of days ago on eBay. I was looking for, just searching through the internet really, sort of spares and repair equipment that needs to be repaired. I don't usually spend this sort of money on test gear, but I sort of splash out a bit on a sort of slightly more modern piece of test gear. And this is an Agilent E3630A 3-rail power supply. Pretty basic model, but of course, like all Agilent HP and Keysight stuff, it's sort of like more expensive than the sort of like cheap Chinese stuff, and you'd expect obviously better quality components fitted inside. So basically, this is a linear power supply, which basically means it's got no switching noise. It's all done with a transformer and a linear regulator, old conventional type sort of regulation system. A big advantage of that is it's very electrically quiet. There's no switching noise, so if you're working on transistor radios and things, you won't get any noise coming through. The big disadvantage of it is it's limited on what it can do for power wise, because basically you're dissipating the losses you're dropping from the regulator are dissipated in heat, and therefore they get very hot very quickly, so they need usually larger transformers and big heat sinking. So this sold as spares or repair, and I thought, well, it'd be a nice little project to see if we can get it going. When I got it, it was in pretty good condition, it was, but I've cleaned it all up and it's come up really nicely. There's a bit of sort of like labels, glue still stuck on it. So what it is we've got here, we've got a plus and minus 20 volt rail with capability of ½ an amp, and a plus 6 volt rail with a capability of 3 amps. Is that 3 amps? Yes, it is 3 amps. No, 2.5 amps, sorry, 2.5 amps. So for transistor radio work and sort of amateur radio gear, handhelds and things like that, it's probably fine. You're very limited on current capability on the 20 volts, but the 5 volts is, you know, reasonable. 2.5 amps is pretty reasonable for a 6 volt supply. Probably not enough for sort of like computer gear, but certainly for sort of like transistor radios and sort of lower powered stuff where you're working with chips and things like that, it's absolutely perfect. So what we've got here, we've got a common output really. Basically we've got a common 0 volt connection for the plus 6, plus 20 and the minus 20. We've got a control on the left hand side here that does the adjustment for the 6 volt, and the control here that does the plus and minus 20 volts, and they track together. So basically if that pot's sort of that position, it's at 16 volts here, it should be 16 volts on the minus. There is a tracking control here that's got a center indent, or not center indent, a far indent off, which basically means that in the off position those two rails should be exactly the same, but there is a tracking ratio here that allows the minus 20 volt rail to drop below the plus 20 volt rail. So for example, if you're doing a plus 20 and a minus 18 volt, you can adjust that tracking control to get that correct offset, or that balance if you want. And likewise, if it's the other way around, you just swap the polarities of your 0 volts around, and then you've got the tracking the same. So 5 volts is pretty straightforward. It's 5 volts and that's it. There's no current control on here. Your fixed is constant voltage until it gets into current limit, and where it will fold back. It's a fold back system, whereas I mean by that is when it achieves its current limit, the voltage will just sort of tail it off as you try and pull more current out of it. Some of the more elaborate power supplies have got the ability to sort of like do a dropout system. So when you pull more than sort of like the current limits of say ½ an amp on the right hand channel, when you're putting more than ½ an amp out of the 20 volts, the output will just drop off and cut out. You know, it's like a safety thing. But on this power supply, it will just limit itself to current to ½ an amp, and it will do that by dropping the voltage back. So you will never dissipate more than ½ an amp. You'll probably find that the current limits are actually set slightly higher than that, but we shall look at that in a moment. So I suppose the first thing to do, I've been around it, I've checked it's set at 240 volts. There's no obvious damage on the case or anything. Is to power it up and see if it works. So it's connected up to the outputs, and it's via a 2 amp fuse. Let's plug it in, see what it does. I'm not that keen on soft starting things like this. I think I'd just rather turn it on, and if it goes pop or it doesn't do anything, you know, that's fair enough, because I'm sure the person who sold this has plugged it in, switched it on, and said it didn't work. So let's find out exactly what's wrong with it. So switch it on. Okay, and first of all, it's got some strange readings here. -5 volt. Oh, okay, we haven't got anything selected. Okay, so this is the 5 volt rail. Okay, that looks normal. jittering about plus or minus. That's fine. So in theory, if we turn this up, we should see a 5 volts and that looks like that's working okay. Then we've got the normal sort of like jitter on the ammeter, which you'd expect. Nothing connected at the moment. So that looks like it's working fine. It goes up to almost 7 volts. So yeah, that appears to be working fine. Can't see anything wrong with that. Let's go plus 20. So we need to turn this control. And that looks working. It's like it's working as well. 15. Goes to 23 volts. Turn it right down to nothing. And it goes down to 0. Okay, so in theory now, then if I set it to, okay, 6.27. If I press minus 20 volts, it should be 6.27. And it is. Okay. So it looks like the minus and the plus volt rail is working correctly if the meter's to be believed. Obviously got no current flowing, which is what you expect. So let's try the tracking control. So we set out 20 volts to, let's set it to 10 volts, about 10 volts. This is one thing I don't like about this. This is a single turn pot, and for a 20 volt range, when it goes down to a tenth of a volt, it's too jumpy. And what I would be interested in doing is seeing if I can fit a multi-turn pot to that. There's your 10 volts. Okay, so we get to minus 20, and we should have minus 10 volts, and we should be able to adjust that. There we go. So let's turn that, for example, down to 5 volts. This pot's a little bit noisy, and it's a bit of a horrible feel to it. Actually, it's got a lot of, yeah, it's sticky. It's all like, yeah, there's a lot of stiction to that pot. Okay, but it's, yeah, okay, minus 4.87. This should still be at 10 volts. Okay, so far everything appears to be working correctly. Obviously we won't know until we put it under a bit of load and check for ripple and noise, but I think the next thing to do is maybe pop the top off and make sure none of the capacitors have vomited anything out. Have a look at the build quality, because even though this is an Agilent, you'd expect it to sort of be a cut above the sort of Chinese stuff. It does have that cheap Chinese plastic power supply feel to it, and that's probably because it has been built in China. I don't know that, I'm not stating that, but I think it has been built in China, and it's probably, you know, it's their idea of not an entry level power supply, but, you know, an affordable power supply for people who want something slightly, maybe slightly better than the cheap Chinese stuff. So let's pop the top off it, have a look inside, and work out if it's got any good bits in it. Right, let's try it on the 20 volt range to start with, and what we're connected up to at the moment is I'll connect that to my loudspeaker dummy load, or amplifier dummy load if you like, and it's set to 8 ohms. So in theory, when I get to 4 volts on the meter, we should be getting close to current limit. It's only capable of half an amp. So if the readings are anywhere near correct, and we'll check this, or we'll elaborate on this a bit later on, you know, with probably some proper loads, to see if it's okay. So run the voltage up and see what we get. You can use the voltage. Okay, there's 2 volts. Yeah, it looks pretty good already. So look at 2 volts for a quarter of an amp. So at 5 volts. Okay, we're not going to get 5 volts. Sorry, at 4 volts. Yeah, we're approaching current limit. This is your half an amp at 4 volts. Now you've got to bear in mind we're taking into the length of the lead, but it looks in the ballpark figure. That's good. Let's try it on the positive rail. Similar. Yeah, 4.12 volts, half an amp. So we're at the limit of the power supply's capability here. So it's a very low power supply, but as I said before, it's linear, and it just has the advantage of being very electrically quiet. So let's switch over to the 5 volts and have a look at our 5 volts. Now, what I'm going to do, I'm going to go to 4 ohms on 5 volts, so we can actually get. We won't, otherwise if we're on 8 ohms we won't even get to an amp. So let's increase our voltage. We'll probably just about be able to get to an amp, just over an amp, before we run out of header volts, or head of volts. There we go. So at 6.91 volts, it's 1.66 amps. So that tallies up really with what you'd expect. So at 4 volts you should be about an amp. It's pretty close, isn't it? You know, I don't know how accurate my dummy load is for the amplifiers, but it's around 4 ohms, and that's clearly perfectly acceptable. So I'm not sure why this was sold as spares or repair, but it appears, on first sort of like look investigation, it's working perfectly well. It's a nice clear display. Yes, it's got that slight sort of cheap Chinese build quality to it. I'm saying anything's wrong with that. It'll be interesting to open it up and have a look inside, see what quality the components are, because initially when I'm working with it, it feels just like a fairly cheap power supply. But let's open it up and have a look inside, see what we've got inside. Okay, here's a look inside. It's got a nice beefy transformer for its output power. What I really don't like is that there's no screws to remove the cover on this unit. You actually just snap get a screwdriver underneath a little corner of the bezel and just snap it off, and it's all a bit nasty. It feels like it's going to break. So let's have a quick look through, see what we've got here. This is what it looks like to me anyway, so it doesn't guarantee it's accurate. We've got a voltage selector switch, line selector switch here for incoming mains, which is nice. That's a nice big clunky switch, you know, rather than having to move jumpers on a tag strip or anything like that. So working from the back here, this looks like it's 5-volt pass transistor, which is surprising. It's a Pt1 device. This is our main rectifier for doing all the rails, as you think, and including the aux and things. This is obviously quite a high current rectifier here. Smoothening for the 5 volts, the main smoothening before it goes into the regulation. These are probably, without checking, these are probably your resistors for detecting current. Various driver stages here. All the capacitors look in nice condition. These are sort of Bourne's multi-turn pots, so you can actually get a good adjustment on the range there. That's good. Down here, we're moving over to the more to the 15 volt, the plus or minus 20 volt rail. There's our rectifiers down here. We've got a couple of TO220 rectifiers underneath this cable here. You see that. It's also actually got, I think, I need to check the circuit again, but I think it's actually got a crowbar protection. And that's quite common on linear power supplies, because if the pass transistor goes short circuit, and so you were pulling a lot of current out, sort of like you're on the 20 volt rail and you're pulling sort of like maximum load out of the 15 volts, and suddenly the transistor goes short, collector emitter short, it will pass the full unregulated supply to your output terminals, and you don't want that. So what will happen is the device will actually fire a crowbar, short the output out, and in theory blow the fuse. That's the purpose of a crowbar. It's a last ditch attempt to sort of break the supply off. That's the only real way you can do it reliably. Obviously, if you've got an inline fuse, it would probably blow, but you know, you can't guarantee that. You're not going to have a fuse. You don't know what the current's going to be when you increase the voltage from, say, like 15 to 20 volts. It's going to go up by probably a percentage, but you know, the only real way of protecting the equipment downstream is to activate a crowbar. So there are your pass transistors there for your plus or minus rail. I expect one's probably an N channel and one's a P channel, depends how it's being wired. There's your smoothening, or as I say, your rectifier. These little white devices down here, these little white sort of like chips, probably optical isolators. I think that's all part of the crowbar, and I think these are probably actually crowbars. Actually, looking at this, the CR28 just here, this and that one there, and there's two there, are probably the crowbars. As I say, they're just there for protection. Got various pots and things like that. We're not going to adjust. So let's have a look at the front panel. And okay, look, that's nice, because the front panel controls are actually, well, they certainly look like you can actually just take one out and put a multi-turn pot in there. So I think that's going to be an upgrade worth doing. Certainly going to make it a lot easier to use, and maybe even do it for both of them. So I think that might be the next part of the video. See if we can change this for multi-turn pots and make this thing a little bit more user-friendly on the front panel. So for the time being, I think that will be the part one of this HP. What is it? It's an HP. No, it's not even HP anymore, is it? It's an Agilent E3630A triple power supply. Thanks for watching.